Now, here's something that surprises many people. Transformers do not keep their weight matrices perfectly orthogonal during training. Every optimization step uses gradient descent to update the weights, so the matrices continuously evolve as the model learns. They are generally no longer perfectly orthogonal. So why do orthogonal matrices matter so much? Because transformers borrow their geometric properties where they matter most. Some models begin training with orthogonal initialization for better stability. Rotary positional embeddings use pure rotations, preserving geometry while encoding position. And some training techniques encourage weights to remain close to orthogonal because it improves numerical stability. Orthogonality isn't a rule that every layer must follow. It's a powerful design principle that helps modern transformers learn efficiently without losing their geometric foundation. Modern transformers contain billions, sometimes even trillions, of parameters. At first glance, it seems obvious. More parameters should mean more intelligence. After all, if every neuron learns something different, the model should understand the world from many unique perspectives. And that's exactly what we hope happens during training. But something surprising begins to happen. As the model learns, many neurons slowly start discovering almost the same patterns. Instead of contributing new knowledge, they begin repeating what other neurons already know. Imagine a classroom with 100 brilliant students solving the same difficult problem. If 90 students write exactly the same answer, have you really gained 100 ideas? Or only 10? This hidden redundancy quietly grows inside many transformers, reducing the diversity of the representations they learn. Now, this is where things become really interesting. I want you to give me your complete attention, because from this point onward, we're not just learning about transformers. We're learning principles that can help build better transformers. If you truly understand these ideas, you'll begin thinking like an AI researcher, not just an AI user. So how do we stop neurons from repeatedly learning the same information? The answer comes from one of the most elegant ideas in linear algebra: orthogonality. Imagine two feature vectors pointing almost in the same direction. They describe nearly the same information. But when the vectors are perfectly perpendicular, each one captures something completely different about the data. Instead of copying existing knowledge, every neuron discovers a new perspective. Suddenly, the same number of parameters can represent a much richer understanding of the world. Notice something remarkable. We didn't add a single new parameter. We didn't make the transformer larger. We didn't increase the computational cost. The only thing we changed was the relationship between the learned features. Instead of repeatedly looking in the same direction, every neuron now explores a different part of the representation space. The result is a richer understanding of the data using exactly the same model size. This is the real beauty of orthogonality. It doesn't make a transformer bigger. It makes every parameter more meaningful. But this is only the first problem orthogonality can help with. There is another challenge hidden inside every deep transformer, and solving it may be even more important. Now, you might be wondering, this idea sounds beautiful. But how do we actually teach a transformer to learn orthogonal features? The answer is surprisingly elegant. Every layer inside a transformer is represented by a weight matrix, and every column of that matrix can be thought of as a direction in the feature space. During training, some of these directions slowly become similar, causing neurons to learn redundant information. To prevent that, we encourage the weight matrix to satisfy one simple mathematical condition. W transpose multiplied by W should become the identity matrix. This tells the optimizer that every feature direction should remain independent from the others. It doesn't force the network to memorize anything. It simply encourages every neuron to learn something different. This single mathematical constraint transforms the beautiful geometric intuition we just saw into something that can actually be optimized during training. Now let's discuss the second problem that we briefly mentioned while discussing the first one. This problem is called vanishing and exploding gradients. To understand it, we first need to understand how a transformer learns. After making a prediction, the error travels backward through every layer. This process is called backpropagation. As the gradient moves backward, every layer multiplies it by its weight matrix. Now imagine this multiplication happening not once, but hundreds of times. If the singular values of these matrices are smaller than 1, the gradient becomes weaker after every multiplication until it almost disappears. The early layers stop learning because they receive almost no training signal. This is called the vanishing gradient problem. But if the singular values become larger than 1, the opposite happens. The gradient grows larger and larger at every layer until it becomes unstable. This is known as the exploding gradient problem. For many years, these two problems made training very deep neural networks extremely difficult. Modern architectures address them using several techniques, including residual connections, normalization, better initialization, and one beautiful mathematical property called orthogonality. An orthogonal matrix has all of its singular values equal to exactly 1. That means the gradient neither shrinks nor explodes. It simply flows through the network, preserving its strength from one layer to the next. Throughout this video, we kept talking about singular values. They determined whether gradients vanished, exploded, or remained perfectly stable. But have you ever wondered where these singular values actually come from? Why do some directions stretch while others barely change at all? The answer lies in one of the most beautiful ideas in linear algebra: eigenvalues. In the next episode, we'll uncover how eigenvalues quietly control the flow of information inside every transformer.